So today we're going to be looking at the molar conversion factors, but using the same system that we used last week and last time for compounds in balanced equations. So let's start with our first equation. Given 15 moles of silver 1 iodide, how many moles of iron 3 carbonate are required to fully react? How many moles of iron 3 iodide and silver 1 carbonate will be produced? You're given a balanced reaction here. Remember, you're going to be given some form of balanced reaction or some form of reaction. Always double check that it's balanced. Don't assume that you were given a balanced reaction. So I tend to highlight as I read word problems because especially like in chemistry word problems, sometimes there's a lot of words that you just don't need. So if you're reading a word problem, I tend to highlight in 2 different colors, one of like my givens, and then one that's like what I'm looking for, so I can visually see the information, and I can also break it down separately. But it's a trick I use. If you're doing any kind of word problem, my son gets these lovely like 2-sentence word problems that he thinks are the hardest things ever, that are like, what is a quadrilateral with 4 sides that are equal? And it's like a square.
Why did I know that? Quad is 4. 2 equal sides. No, 4 equal sides. 4 and 2. 4 is 4. Oh.
So if it's 2 equal sides, it'd be a rectangle. It's 4 equal sides, it's a square. But I tell him the same thing that I'm telling you, so I'm giving you the same hints. It doesn't matter if you're doing word problems for math, if you're doing word problems for chemistry, if you're doing word problems, I don't know, for English. If you highlight the important information, you can take out all the stuff that is fluff. So, given, I'm going to highlight in yellow for my givens, given 15 moles of silver iodide. So our given is 15 moles of silver iodide. How many moles of iron 3 carbonate? We care about moles of iron 3 carbonate are required to fully react. Doesn't matter that it says all those words. We're going from moles silver 1 iodide to moles iron 3 carbonate. That's really what that means. How many moles of iron 3 iodide and silver 1 chromate will be produced? So we're going to moles iron 3 iodide, moles carbonate. So of all of these things, the only really important things are the things that I highlighted. So you can kind of focus in on what's important. Hey, I know this is all words, but at this point in chemistry, you should be able to like go silver 1 iodide. Oh, silver iodide. Iron carbonate. Iron, like you should be able to at least match up the compounds with what's written. So you were given 15 moles of silver 1 iodide, so you put the 15 mole over to where your given would be, because that is your given. Remember, if you're following this, your given's usually the A's, except if you're going from moles to grams, then your given is the B's. Then we're just going from moles to moles, so we set up our molar conversion. And because we have mole silver iodide here, we have to have mole silver iodide down below, so you can go ahead and cross it out. And we get these moles from our balanced compound. So looking at our balanced compound, we end up with 6 mole silver iodide. We're going at first to moles of iron 3 carbonate. So we look at iron carbonate here. Make sure that you're writing it out as mole Fe2CO3 3. And while we're doing that, it's written one time, there's no coefficient, so we know it's 1 mole iron carbonate because there's no coefficient. When there's no coefficient, you assume 1. So 15 times 1 is 15 divided by 6, leaves me with 2.5 mole iron carbonate. The same problem, we asked, given the same amount of moles of silver iodide, how many moles of iron 3 iodide? So we're still given 15 moles of silver iodide, so that still goes over on the left. A common question I've had asked is, do these get added up at the end? No, they're all separate. These are all separate from each other, so they're independent. Given this, I need that. Given this, I can produce this. Given this, I can produce that. But they're not added up or related to each other in any way outside of given this to that. They don't at the end get added up or anything. That was a very common question. I never even thought of that question until someone asked me, so I figured I would just get ahead of that. So we given moles silver iodide. Remember, the moles have to cancel out, so I end up with mole silver iodide down here. You're again relating to the balanced equation, so that's 6 in front, our coefficient. That coefficient is the number of moles, so I put 6 mole silver iodide. Then we're going to go ahead and go to moles iron 3 iodide. Look here, we have 2 mole iron 3 iodide. So we multiply across 2 times 15 times 2 is 30. 30 divided by 6 is 5. So we end up with 5 mole iron 3 iodide. Okay, you guys are given the challenge to try the last setup on your own. I'm going to walk you through it. You are still given 15 moles of silver iodide. But now we're looking for moles of silver 1 carbonate. So again, we're starting up our mole ratios. And remember, your mole ratio goes to everything. So if we're looking at mole ratios, this is a 6-to-1 ratio, this is a 6-to-2 ratio, this is a 6-to-3 ratio. Don't simplify mole ratios. This is a 1-to-6, a 1-to-2, a 1-to-3. We don't simplify mole ratios. We use the numbers, even if it looks like it should be simplified. A 3-to-6 ratio will remain a 3-to-6 ratio because of where you're getting your numbers. So we're looking at silver iodide. We still have 6 moles of silver. Remember, these are from your balanced equation, or if you're using a compound, these are from your balanced compound. And now we're looking at moles of silver carbonate. That 3 out front is a 3 mole silver carbonate. So we put the 3 mole here. Now we multiply across. 15 times 3 is 45. 45 divided by 6 gives you 7.5 mole silver carbonate. These are your 3 answers from this one setup. These 3 are independent of each other. It's just given this amount of moles, you need this much to fully react with that many moles. And given these moles, this is how many products you can from these reactants. Okay, let's try our next setup. How many grams of calcium sulfide was used to produce 15 moles of vanadium sulfide? So, again, yellow to highlight what we have. How many grams of calcium sulfide was used to produce? So we do not have grams. We have 15 moles of vanadium sulfide. This is what we have. We're looking for grams of calcium sulfide. So going from moles to grams. Then the next thing is we were given this equation, but on a first glance, it doesn't appear that it's balanced because I have 5 oxygens over here and only 1 oxygen here. So I need to balance my equation. So I'll give you all a second to balance it. When balancing this equation, it's one of those ones you can kind of easily do in your brain. We have 5 oxygens over here, so we only have 1 here. This is a 1-to-1 ratio for the calciums. So if I put a 5 out front here, that gives me 5 calcium and 5 oxygen. If I look over here, I have 5 sulfurs. If I put 5 out front here. That still gives me 5 calciums, 5 sulfurs. Now I'm balanced. So an important thing that I always do is that if I'm looking for grams or I'm given grams, I always immediately find molar mass. There's no if, and, or but. I don't wait till later to do it. It's just that check mark off that if I'm given molar mass or I need to find molar mass, or I mean grams, given grams, I always do molar mass. So we need grams of calcium sulfide. So my first step is to find molar mass of calcium sulfide. And we've done this before. I'm just going to remind you of the steps. Remember, the first thing you do is separate your compounds. So I have calcium and I have sulfur. I tell you how many moles are in each part of the compound. I have 1 mole of calcium. I have 1 mole of sulfur. So I go ahead and write that out. The next thing I do is I go ahead and I look up the molar mass of each item on the periodic table. 1 mole of calcium is 40.08 grams per mole. And 1 mole of sulfur is 32.07 grams per mole. Once I have that sorted out and looked up, I multiply across. Moles times grams gives me grams of element towards that element, total element. So I have 40.08 grams of calcium and I have 32.07 grams of sulfur. I go ahead and I add them together for my total molar mass, which ends up being 72.15 grams per mole. And remember, it's grams for every 1 mole, especially when we're looking at things in terms of dimensional analysis and molar ratios. And that's grams per mole of calcium sulfide. Now that we have our molar mass, we can go ahead and convert our moles to grams. So remember, as always, we take our given and we put it to the left-hand side. So we have 15 mole silver, nope, I went on autopilot. We have 50 mole of V2S5. Now we have mole V2S5, so that means we have to at least convert to moles first, because when you're given moles, you always have to use a molar ratio unless you're going to grams. And we're not going to grams, we're going from mole A to grams B, so you always have to go through moles first because moles are the only unit that has a direct ratio. So, because we have moles V2S5, the moles have to go on bottom so that they go ahead and cancel out. So we end up with mole V2S5 on the bottom. Looking at our balanced reaction, we have 1 mole V2S5. Now we're going to go ahead and look at where we're converting to. We are converting into moles of calcium sulfide. From our balanced reaction, we have 5 moles of calcium sulfide. Now, if we were going from moles to moles, we'd stop here, but we're going from moles to grams. So we have to set up another conversion factor. And seeing we have moles calcium sulfide on top, moles of calcium sulfide must go on the bottom. So I go ahead and I put in 1 mole calcium sulfide, because we know when using molar mass, it's always grams for every 1 mole. We can go ahead and reference the molar mass that we already solved for and pull that down into this equation. So that's 72.15 grams. And a nice trick to checking if you're doing this setup right is asking yourself, does everything cancel but the units I'm looking for? So we're looking for grams calcium sulfide. So the units you're looking for should always be in this final part right here. And then everything else should cancel. So moles V2S, mole V2S, they cancel. Mole calcium sulfide, they cancel, leaving you with grams. That's not always going to get you to 100% the right answer, but it's going to at least make sure that you have the right setup. Once you do that, remember you multiply across and divide down. So 15 times 5, 15, 30, 45, 50, 60, 75. divided by 1 is 75 times 72.15 divided by 1 leaves me with 5,411.25 grams calcium sulfide. Given 432 grams of boron hydroxide. It says given right there, so we can go ahead and already highlight our given. How many moles of boron sulfate, so we're going moles of boron sulfate. That's not a highlighter, that's a pen. Moles of boron sulfate and grams of dihydrogen monoxide will be produced. So it looks like we're going from grams to moles and then grams to grams. We also want to know how many grams of sulfuric acid will be required to fully react. That's important, but we want to know how many grams of sulfuric acid. So it looks like we're doing, this one's a 3 setup. We want grams to moles, grams to grams, and grams to grams. So, as always, when you are given grams or when you're looking for grams, the first thing you do is set up your molar mass. When you're given grams or you're looking for grams, your first step is to always find the molar mass. Now, a big trick that I like to do is, especially when I'm doing a balanced compound, because a lot of the elements are the same, is find the molar masses in tandem with each other. And I'll show you what that means, but it'll make sense once I show you. So, we need the molar mass of boron hydroxide. So, molar mass boron hydroxide. And remember, you never use it 2 up front. You're finding the molar mass of 1 mole, so you don't multiply it by your coefficients. And the first step for this is to go ahead and break it apart. We have B, O, and H. And for the B, we have 1 mole of B. We have 3 mole of oxygen. And we have 3 mole of hydrogen. Once I've done that and separated my moles, I go ahead and I set up my next one. So we need the grams of dihydrogen monoxide. That means we need the molar mass of dihydrogen monoxide, and that's just a fancy term for water. So we need molar mass of H2O. And you can go ahead and separate it out. We got H and O. We have 2 moles of H, and we have 1 mole of oxygen. We also need a molar mass of sulfuric acid, so we set that up too. Now, if you're wondering why I tend to do the setups like this and then go back and do the grams, it is because if you look here, we have oxygen, oxygen, oxygen. I can look it up 1 time and then put it in for all of them, so I'm not working so hard. So we have H, we have S, and we have O. So for H, we have 2 mole. For S, we have 1 mole. And for oxygen, we have 4 mole. Now, after that, we go ahead and we add in the grams of all of them. So we look it up on the periodic table to get the grams. So look, there's only this 1 boron, so we can do that first because that's a singular lookup. So we have, look up the periodic table, and boron is 10.81 grams per mole. Now we can look at oxygen. Now look, oxygen is here, here, and here. So when we're looking it up on the periodic table, we can look it up 1 time and put the number in for 3 times. So working smart, not hard. So when we're looking at the molar mass of oxygen, is 16 grams for every 1 mole. And I can put that number here, here, and here, because we can look up the number 1 time and use it in 3 different spots if we're working in serial. And that's why I always say to do all this work at one time because a lot of the time, a lot of the numbers are going to be the same. So you're looking up hydrogen, like hydrogen's here, here, and here. So you look it up one time and you can put the number in 3 different spots instead of having to continually re-reference your periodic table. So we have 3 mole. We look up at the periodic table. It's 1.008 grams per mole. We can put that here. And we can put that here. That leaves me with the only other singleton. So of all of these things, there are only 2 items that weren't used again, and that would be boron and sulfur. We look up sulfur, it's 32.07 grams per mole. Once we have that, we can go ahead and solve for the grams total. So remember, you multiply across. So 1 times 10.08 gives me 10.08 grams of boron. 3 times 16 gives me 48.00 grams of oxygen. Always put in your placeholders. And 3 times 1. Oh, I know I said, oh wait, it's supposed to be 81. I was looking ahead to, that's a 1, pretend that I can math today. And 3 times 1.008 gives you 3.024 grams of hydrogen. Go ahead and just do all of this one math first, and then you go through and you add it up. I do it in serial, especially when I'm doing it all together, so it's all of one step, then all of the next step. It makes your life a lot faster. So 2 times 1.008 gives me 2.016 grams of hydrogen. 2 times 16 gives me 16 grams of oxygen. That's an H. Then we go ahead and keep doing that. 2 times 1.008 gives you 2.016 grams of hydrogen. 1 times 32 gives you 32.07 grams of sulfur. Finally, 4 times 16 gives you 64.00 grams of oxygen. I always put the .00s in, or I try to remember just for placeholders, but if you forget, it's not going to like affect your math. It's just, especially if you're trying to do math quickly or check your work, sometimes the placeholders can get funky. Remember, you add them up, so you add 10 plus 48 plus 3.024, and you end up with 61.834 grams per mole boron hydroxide. I should have left more space. I'll make sure I do it here. We're going to add all of these up, and we end up with 18.016 grams per mole H2O. And then you add up all of these, and you end up with 98.086 grams per mole H2SO4. And now you've done potentially, and honestly, the most time-consuming part of any setup is finding the molar mass. Once you've done that, and if you did all at the very beginning, all the setups should go very, very quickly. Okay, let's start working through these now that you've had a chance to try them on your own. So the first thing we're doing is going to go from our given. So we were given 432.84 grams boron hydroxide. So we're going to put that again on the left, because you put your given on the left so that you can start from there. So we were given 432.84 grams boron hydroxide. And our first step is that we're going to moles of boron sulfate, but you can't go from grams of this to moles of that without finding moles of this. So if you're given grams here, your grams have to go on the bottom. So grams BOH3, which we pull from our molar mass, so 61.834. 61.834 grams, and that's grams for every 1 mole. Now that we have that set up, we can go ahead and set up the mole ratios from our balanced compound. This is mole BOH3. So we look at our balanced compound. We have 2 mole BOH3 from that coefficient. So we put 2 mole BOH3 on the bottom so that they go ahead and cancel out. And we're going to moles of boron sulfate. So we have boron sulfate, which is a 1-to-1 ratio. So we have 1 mole B2SO4. And then we go ahead and we multiply across and divide down, and we multiply across and we divide down, and we end up with 3.5 mole B2SO4. Now that we have this set up, let's go from grams boron hydroxide to grams dihydrogen monoxide. So we still start with the same number of grams. So we start with 432.84 grams boron hydroxide. And now we have to go to grams of something else. But if we're given grams, the first step is after going from grams to moles. So this is where we use molar mass. So again, we re-reference our molar mass from what we solved for, and that's still 61.834. So we go ahead and put that on the bottom so that the grams go ahead and cancel out. So we have 61.834 grams boron hydroxide. Grams cancel out. And that's for every 1 mole of boron hydroxide. Now that we have that set up, you remember always have to go through a molar conversion. You can't just go from grams to grams or moles to grams. You have to always go through a molar conversion. So we have mole boron hydroxide on top. We have to put moles of boron hydroxide on the bottom. We pull it from our balanced equation, and it's 2 moles boron hydroxide. So we put 2 mole BOH on the bottom. And we're going to water, so we got to pull our moles of water. So on the top we have, from our balanced equation, we have 6 moles of water. So we put 6 mole H2O. Now if we were doing grams to moles, this is where we would stop, but we are going from grams to grams, so we have to add a third conversion factor. And remember, we solve for the molar mass of water, so we have mole H2O. We put 1 mole H2O on bottom because the molar mass is every grams for every 1 mole. And we go ahead and we're going to go ahead and put the grams for H2O at top that we solve for, which is 18.016. And we multiply across and divide down, and we multiply across and divide down, and multiply across and divide down, and we end up with 378.84 grams H2O. And for our final setup, we're looking for grams sulfuric acid, but we're starting from the same spot. So we start with 432.84 grams boron hydroxide. Again, that goes to our left. And then our next setup is going from our grams and then using our molar mass to go to the moles. So it's the similar setup. The molar mass is still 61.834. This number is what we solved for when we solved for our molar mass earlier, 61.834. So put that 61.834 grams boron hydroxide. Remember, that's because the grams to the grams are going to cancel out. That's for every 1 mole of boron hydroxide. Then you're going to go ahead and set up your molar conversion, because you always have to be converting through moles. Remember ABCM, always be converting through moles. If you look at our balanced reaction, we still have 2 moles of BOH, but we have 3 moles H2O4. That 2 mole BOH goes on bottom. And that 3 mole H2SO4 goes on top. Remember that things can cancel out. If we were going to moles, we would stop here, but we're going from grams to grams, so we have to do the 3rd conversion factor. Mole H2O4, if we're going to grams, remember it's molar mass, it's for every 1 mole H2SO4 that has to go on bottom so that they could cancel out. Then I go ahead and I put my molar mass on top from what we solved for, and that would be 98.086 grams. And then I go ahead and I solve by multiplying across and dividing down, and multiplying across and dividing down, and multiplying across and dividing down, and I end up with 1,029.91 grams of H2SO4, and this is how we do full molar conversions for a balanced reaction.